Good day everyone! For today's video, I'm going to show you my video presentation on what we learned about spherical geometry. We are asked to create a triangle in the surface of the sphere, compare plane Euclidean geometry and spherical geometry, and lastly, apply spherical geometry in real life. So before that, let's us define what is spherical geometry. So, spherical geometry is a study of geometric objects located on the surface of a sphere. Spherical geometry works on similarly to Euclidean geometry in that there still exist points, lines, and angles. For instance, a line between 2 points on a sphere is actually a great circle of the sphere, which is also the projection of a line in three-dimensional space onto the sphere. So now let's proceed. So, our first task is how to create a triangle in the surface of a sphere. Here is my example. So, if we have a point ABC here, then we can have one side of a triangle here, and other side of a triangle here, then other side over there. So as you can see that we can picture out that there would be a three right angles in this triangle. So what I am doing here is I'm trying to introduce to you the idea of spherical geometry. And so this is how you visualize on the surface of a sphere. Okay, let's move on to our next task. Our next task is to compare plane Euclidean geometry and spherical geometry. So, in the plane Euclidean geometry, there is a unique line passing through any 2 points. While in a spherical geometry, there is a unique great circle passing through any pair of non-polar points. So, a line goes on infinitely in two directions in a plane Euclidean geometry. On the other hand, a great circle is finite and returns to its original starting point in a spherical geometry. So, if 3 points are collinear, exactly is one between the other two in a plane Euclidean geometry, as you can see in my example. So, for example, we have point A, B, C. So, B is between A and C. So, in a spherical geometry, if 3 points are collinear, any one of the 3 points is between the other two. So, in my example, if we have point like this, so we consider that ABC, so we have A is between B and C, and the other two is B is between A and C is between A and B. So a line segment is the shortest path between 2 points in a plane Euclidean geometry. While in a spherical geometry, an arc of a great circle is the shortest path between 2 points. So next would be two lines intersect at one point and form four angles in a plane Euclidean geometry. And in a spherical, two lines intersect at 2 points and form 8 angles. So, through a point, not on a line, there exists one parallel line on a plane Euclidean. While on the other hand, no parallel line exists in spherical geometry. So, perpendicular lines form four right angles in a plane. And while on the spherical geometry, perpendicular lines intersect twice and form 8 right angles. So, both plane and spherical geometry has three non-collinear points form a triangle. But in a plane Euclidean geometry, triangle sum is 180 degrees. While on spherical geometry, the triangle sum is greater than 180 degrees but less than 540 degrees. So, in a plane Euclidean, a triangle can have at most one right or one obtuse angle. But in a spherical, a triangle can have more than one right or obtuse angle. And lastly, in a plane Euclidean geometry, each angle of an equiangular triangle measures 60 degrees. but the angle measures of an equiangular triangle can be varied in a spherical geometry. So the next slide would be our last task. That is how to apply spherical geometry in real life. So spherical geometry is useful for accurate calculations of angle measure, area, and distance on Earth. The study of astronomy, cosmology, and navigation, and applications of stereographic projection throughout complex analysis, linear algebra, and arithmetic geometry. Whether or not they know it, nearly everybody relies on spherical geometry sometime. Just consider the way to chart a plane's course. For example, pilots and sailors use it all in their job to find the shortest path to their destination. Remember that Earth has a spherical form and therefore the Euclidean rules of the plane applied to the surface of the planet won't work like that. This means that the shortest path between Washington and Moscow on the Earth's map is not a straight line, but rather a curved line that follows a line on the sphere that is Earth, as you can see it in this presentation. So, the pilots who deal with spherical geometry on a daily basis have to go through these mathematical calculations along with other more complex derivation every time they want to analyze the direction or the path of their journey. So that's the end of my test. Thank you for listening to my video presentation. I am Bibsy Kanson, your BSED Math presenter. Thank you.